We'll talk about instrumental variables and causation. Causation is one of the big overarching questions we're going to come back to again and again and again and again. It's one of the superpowers that economists bring. Practice thinking about causation and being wary of simplistic notions. Machine learning technicians or people in various aspects of data science might not have had a similar kind of focus. They're just finding really subtle correlations. You've surely heard the saying, correlation is not causation. We're going to work through some of that. I'll pause to let you appreciate the XKCD comic. Really, the whole strip is like required reading. To assess causation, you need to have a deep knowledge of how the data is generated, as well as solid economic theory about how people are making the choices that we observe. Correlation does not imply causation, but in many cases we believe the logical inverse is true. If something's not correlated, then that implies it's not causal. Granger causality. If two data series are not even correlated, then one certainly can't be causing the other. If I'm flicking a light switch up and down, and the light stays on, nothing happening, then that's evidence that the light switch does not control that light. It might control something else, or it might not be connected to anything, but it's not causing that light to switch on or off. In our regression models, we want X variables to be exogenous. Remember, exo, from outside the model. They're predetermined or set outside this particular econometric specification. So we can draw a causal arrow from X to Y and say X causes Y. We can run into problems if Y causes X, or if there's circularity that both X causes Y and Y causes X. Then we can see a lot of correlation, but we're not going to have any luck identifying causation. We get spurious regressions where it looks like there's something there, but there's no link. In time series, one of the ways we get around this is if a variable is predetermined. Maybe X and Y loop in and cause each other, but if the X variables are from time t minus 1, some previous time period, and Y is observed at time t, then we can say, okay, because of what physics calls the arrow of time, the Y variable today could not get in a time machine and cause X value yesterday. Maybe X and Y today are linked. But if one is predetermined, then we can assert causality. One of the easiest mistakes when you're starting off in econometrics is to regress a price on a quantity or a quantity on a price. We spend so much time in 100 level economics talking about how price change causes quantity to change, but we know it's also true that quantity change, like a supply shock, can cause the price to change. They're interdependent. In theory, we can draw a demand curve, and in theory, we can draw a supply curve, but in actuality, we only observe the intersection. That top panel there is what we have in our brains. It's been so ingrained, it's easy to forget that we do not see the demand curve. We do not see the supply curve. All we see is that one intersection point. If the supply curve shifts outward and the demand curve shifts downward, then the intersection point shifts down while the quantity shifts, well, it depends. Could increase or decrease. We only observe those two little dots in the bottom panel where there were intersections of supply and demand curves. And if supply and demand move again, then we'd see a third dot. You should be getting the sense now. These three dots in the bottom panel are not cohering into anything. If the supply curve keeps shifting around and the demand curve keeps shifting around, then even if I keep observing this till the end of time, I'm just going to see a cloud of points. I'm not going to see a supply curve. I'm not going to observe a demand curve because I haven't pinned down one or the other. The model is not identified. Go back to baby micro, probably one of the first weeks of class. If there's a model with linear demand and supply, then we solve for equilibrium. The demand curve will represent A minus BQ. The supply curve is C plus DQ. And now this part is maybe not baby micro, but we'll add an error term for each of those curves. Solve for the intersection. For now, to make it a little simpler, I'll pick some numbers, make it easy. Q star is 5 plus the average difference in the errors, And the price P star is 5 plus the average of the errors. But those errors are just going to be random. They're not going to show me anything. I'll just see a cloud of points like in the top panel. Supply curve moves and the demand curve moves and there's an equilibrium achieved, but I only see the equilibrium value. Now there is some hope if, for example, the supply errors were a lot smaller than demand errors. For example, if they were 4 times different, then the variation in demand curve would be much larger than the variation in the supply curve. Demand would be really moving around a ton, but only a slight variations in supply, and you can see there, I could allow me to identify the supply curve. But that just moves the question a bit back. How do I know? Why would I think that there's so much larger variation in demand than supply? If you don't have a plausible explanation for why one of the curves is shifting a lot and the other is stable, then you don't have any causation. But still, we commonly see people, unfortunately, put up a cloud of data points, draw a line through it, and if the line has a positive slope, they assert, hey, I've discovered the supply curve. And if it has a negative slope, then, oh, that must be the demand curve. But from a cloud of random points, there's no reason to expect to see either one. The slope of the regression is going to be a random number. And if it's big enough in one direction, maybe it'll get called one thing, and if the random number is big enough in a different direction, it gets called something else. That way lies madness. Now, one common approach in economics is what's called instrumental variables. These are quite contentious, but it's worth understanding the issues. Suppose we want to identify y, which equals, here we keep it simple, beta naught plus beta 1x plus some error. But they're endogenous. X causes y and y causes x. There's circularity. Suppose we had some variable z that's not correlated with y, but it does cause x. Then we could do a preliminary regression. X is gamma naught plus gamma 1 z plus some different error term. Estimate x hat, the predicted values of x, not the actual x variable, but its prediction. We then use those predicted values in the regression of y on x hat. Now this is a bit of, suppose I had some magic z that would fix all my problems. Is there any chance of finding that magic z? It took economists a long time. One of the early uses back in 1930s was looking at the supply and demand for wheat and asserting that the supply could be instrumented with rainfall, since good or bad weather produces a supply shock of a better or worse harvest. If rainfall changes the supply curve, while demand is relatively constant, then, as we showed previously, we can identify the demand curve. The magic z has to be relevant. There needs to be a correlation between z and x that's different from 0. But the magic z also needs to be exogenous. The correlation between z and the errors should be 0. We should be able to exclude z from the list of variables that cause y, so we can have that instrument. More generally, we can look at the case where y depends on a bunch of things, we'll call w, which are genuinely exogenous, but also depends on x, which is endogenous. We want some set of z instruments that explain x, but are not causal for y. If we have more than one z variables with only one x, that's great. If there are multiple x, then we cannot have fewer z than there are x. If there are more z than x, the regression is over-identified. It's just identified if there are just as many z as x, and fewer z would be under-identified. Now, on the other hand, too many controls can also be a problem, particularly if the control variables are a mechanism by which some influence might occur. For example, looking at wages, we want to see what is the differential between male and female wages. We know that women have lower average wages than men. That's partly because women are more likely to work in occupations with a lower average wage due to legacies of gender discrimination. So controlling for occupation might wash away some of the variation of gender in that outcome. In the past, for instance, boys are more likely to become doctors, while girls are more likely to become nurses. And they get paid different amounts. There might be zero difference within the occupation, Men and women who are doctors get the same wage. Men and women who are nurses get the same wage. But if there's, I don't know, a 2-to-1 ratio male to female among doctors and a 1-to-2 ratio male to female among nurses, there's still going to be a difference in the average wage. The average wage of women is going to be lower than the average wage for men because they're pushed into different occupations. But if we control for occupation, that would show they're making the same wage. We'd miss that disparate sorting into occupations if I control for occupation in regression. So there's a balance of controlling for many things, but not too many things. There's some artistry required there. Now, instrumental variables are a form of two-stage least squares. Step 1, use the magic instrument z to regress x on z and get x hat. Step 2, regress y on the exogenous w variables and the x hat and interpret the coefficients. In step 1, we also often worry about weak instruments. There's a rough rule of thumb that we want an F statistic bigger than like 10 or something. Example. There's a paper published in the journal Economic Inquiry on beer consumption and economic growth. I got similar data and put it in the class page for you to play with. We have an issue if we want to estimate a regression explaining state growth of GDP as a function of some exogenous stuff, such as lagged GDP growth, that's predetermined, and beer consumption per capita. Does beer consumption promote economic growth? Or is beer just not an inferior good, so richer people drink more? Clearly both, right? The causation goes in both directions. The authors propose using the beer tax rates that vary state by state as an instrument, because a higher tax reduces demand. So step 1 regression is to explain beer consumption per capita as a function of the tax rate on beer and get the predicted values of beer consumption in each state and each time. Then use those predicted values in the regression explaining economic growth. We can fine-tune some of the estimation procedures. R has packages to help that. I won't give away the answer, in part because I don't think there is a good answer. The paper proposes that beer is bad for the economy, but I couldn't replicate that finding. Best ways to understand instrumental variables is consider some examples. They're contentious in many cases. I don't want you to understand, oh, that's the answer. Rather, they're one answer, one way that economists have tried to provide an answer, which people might believe more or less. Using rainfall or weather as an instrument for crop prices, that's classic. Similarly, to understand the elasticity with respect to price of demand for cigarettes is to use variation in tax rates, just as we talked about for beer. Economists use random variation in births to find the effects of class sizes on education quality. That's tough, because if I ask, are smaller class sizes good for students, that's complicated. There's a lot of variation just from resources. Some school districts are relatively well-resourced, and they're going to have small classes. They'll also have other things going on in the district, in which case students would have good outcomes. Contrast other school districts have fewer resources, bigger classes, other stuff going on in that district and in those families, and worse outcomes for the kids. Joshua Angrist, who got Nobel Prize, found that Israel had a policy that by law there could only be 40 students in the class. By random chance, if there were 39 kids of one age, they'd be in a big class. But if there are 41 kids, then the class would get split in half, and suddenly the kids would each be in a small class. And that enabled get an estimate of what is the impact of class size. David Card, another Nobel winner, noted the impact of immigration on wages. That's also difficult. Immigrants don't just go randomly to a particular city in the U.S. Immigrants are savvy. They're going to go to places where there are jobs and high wages and good prospects for future economic growth. So if we look at the correlation between what parts of the U.S. have lots of immigrants and what parts of the U.S. have high wages and lots of jobs, then you might conclude that immigrants are good for employment wages. But a simple supply and demand analysis would think that an increase in supply means a decrease in the wage if demand is constant. Card looked at what's known as the Muriel boat lift. Back in the 1980s, Fidel Castro decided that he was going to allow a whole bunch of Cubans to leave if they wanted. He even emptied out some prisons where a lot of political prisoners were held. Many of them went to Miami. Card looked at that exogenous shock to see what was the impact on the economy after all those immigrants suddenly arrived. It seemed like a positive impact. The supply increased, but also the demand. So there are plenty of places where we know we have problems and we want good instruments. A granddaddy is in macro, trying to understand how interest rates affect the economy. If you just look at the correlations, you'd see often when the economy is doing bad, interest rates are low. When the economy is doing good, interest rates are high. Does that mean that low interest rates are bad for the economy? Or is it that when the economy is bad, the Fed often decides to lower interest rates? Another curious case is smoking. If you look at the data, whether smokers have better or worse health outcomes, people who recently quit smoking are in terrible health. Does that mean that quitting smoking is bad for your health? No. That's just because smoking is extremely addictive. Why does somebody decide to quit? Usually they have a health scare. Medical professionals looked him in the eye and said, if you keep this up, you're gonna die. So they quit smoking. So it's more bad health causes quitting. Other cases, we want to understand, how does schooling affect people's wages? That's a problem because there's some circularity. And for instance, people from wealthier families are more likely to go to college, but people from wealthier families tend to get higher wages too. Does better insurance coverage help people be healthier? Again, complicated, because healthier people are more likely to get a good job with benefits. So there's correlation there. There are lots and lots of cases where we have tangles of causation and we want to find ways to get at some of the causal impacts.